Welcome everyone to the fourth webinar of SEMLA 2021 webinar series. So after talks by Ben on human-centered AI and talk by Nisha about AI literacy and talk by Vera on explainable AI, today we are privileged to have Danilo and Arif from ThoughtWorks to talk about the continued delivery of machine learning systems. And later in this week, we will have a talk by Nino on AI apps. And finally, on July 1st, we'll have a talk by Grace from Carnegie Mellon on architecture AI-enabled systems. So today's talk will be on continuous delivery of machine learning system. The talk will be by Arif Wider and Danilo Sato from ThoughtWorks. So both have co-authored a very insightful and popular paper about the continued delivery for machine learning. And they are professional working for ThoughtWorks. Arif is also a professor of software engineering. So they have a mix of academic, technical, and very practical expertise that they will be sharing with us today. And I'm very excited to hear their perspective on this very important topic. So without further notice, I will invite Arif and Danilo to share the slide and to share their thought on this problem with us.
Great, thank you.
Thank you. Hello, everyone.
Hi. Okay, welcome everyone. Thanks for spending the time with us today. Arif and I will give you a quick introduction to continuous delivery for machine learning, where it came from, where we've been doing it, and some of the technical components for how to implement it, and also some of the challenges that we see trying to do it in real life. A brief introduction about myself. I'm currently the head of data and AI services for ThoughtWorks in the UK. I'm also part of the office of the CTO. And I spent most of my career, 20 years career here in ThoughtWorks, 13 and a half years to be precise, leading many projects in various areas. My background is in software engineering and architecture. And I moved towards data maybe like 6-7 years ago. I've been leading our global data community and more specifically looking after the machine learning projects that we do. And many years ago, I wrote a book as well, DevOps in Practice, trying to show how to apply the principles of DevOps to the real world. So I have a passion for trying to make these concepts more tangible for people to see how it works.
Awesome. So then, hello, everyone, from myself as well. My name is Arif. I used to be the head of data and AI services at ThoughtWorks Germany. So I was kind of the counterpart to Danilo there from the Germany side. And as part of this role, I also was part of the global data leads team. So for ThoughtWorks globally. So I am usually in a lot of exchange with all the different data leads that we have in ThoughtWorks. And as has already been mentioned in the nice introduction, I moved back to academia a couple of months ago. So I'm now a full professor for software engineering in Berlin in Germany, and work for ThoughtWorks on the side, so to say, but still enjoy to deal with actual real world industry problems there. And so overall, I used to work full-time in consulting for ThoughtWorks for a couple of years. And when doing so, I was usually working as a software engineer or data engineer in our clients' data teams. And this is also where I draw my experience from. And with this, I hand it quickly back to Danilo.
Thank you, Arif. I'll quickly talk about ThoughtWorks in case you haven't heard about us. There's not many slides, I promise. We've been growing for like the last 27 years. I remember when I joined, the email going out about us getting to 1,000 people. And now I was looking, we have more than 9,000 already. We've opened many offices since then. Right now we're in 18 countries. You see here many offices. And what we are, like a global technology consultancy. We help our clients, what we call become modern digital businesses. So anything from digital transformation to how to apply data, the actual software engineering and design and product thinking. We try to bring the full spectrum from defining a strategy all the way to implementing it. You might have heard about us from some of the books. We're very passionate about writing and sharing our learnings with the community. Over the history of the company, we published more than 100 books. Many of these became like industry standards. Martin Fowler is our chief scientist. You probably know about him, his work in refactoring, and he's actually one of the signatories of the Agile Manifesto. So applying Agile thinking is something that we've been doing ThoughtWorks since the beginning of the company. And more specific for today, we actually published a continuous delivery book. I was looking at it. It was published 2010, but we've been practicing it probably since the early 2000s. And then Jess and David codified the principles, and this became like one of our bestsellers book. And what we're trying to do when we move towards building systems that have machine learning components to it, trying to apply these principles to these new types of systems. And that's where continuous delivery for machine learning came from. The first time like we wrote about it, we have this publication that goes out twice a year called the Technology Radar. It's free. You can subscribe or you can look on our website. We look at what are the technologies, the techniques that we're actually using on projects. And we have this radar analogy where we place these technologies on the different rings. And CD4ML, like we call it, started out in the trial ring. And this last edition that came out, it finally moved to the adopt ring. And the adopt ring is not something that we take like lightly. Very few blips make it into adopt. And only when we've done it multiple places and we think it's a practice or a technology that we think you should use it unless you have a good reason not to. That's the only time things move into adopt. So if you look at the history of the tech radar, very few blips make to adopt. Many of the blips show up and then they fade. But we managed to get continuous delivery into adopt this year. It's probably going to fade eventually because we're not capturing here all the blips historically. So if you read the tech radar, is always like a snapshot in time. And if you see something missing that you think like, why is it not here? You should look on the website because we might have talked about that already before and the blip fade in. The other thing we published just recently, an ebook we wrote with AWS. We are partners with most of the big cloud providers. And I co-authored this one about how to get ML ops right. ML ops is probably an industry term that you've heard about, probably more than CD4ML. And people ask me many times, like, what's the difference? Is it similar? And I like to talk about it's a similar analogy between DevOps and continuous delivery itself. They are complementary. DevOps came out about the culture of trying to align, the operations mindset with the developer mindset and how to approach it. But continuous delivery was this set of principles for how do you actually implement that culture and focusing on the automation, the tools, the techniques. So it's kind of like that. Like we approach ML ops, I would say CD4ML is our way it ThoughtWorks to implement ML ops. And based on our experience, we think is the right way to do it because we bring that focus on automation as well. And some of the things, as we're doing research for publishing the ebook, like we're trying to find out, like, is this a real problem? Are people having trouble putting data science or machine learning projects in production? Is it hard? Is it easy? And we bumped into a few of these references. This first one talking about 87% of data science projects never make it to production. Many of them, because they are experiments, they shouldn't make it into production. But 87 is a pretty high number. I'm sure there's lots of useful things in that number that should make it to production. But as we'll see later in the talk, it's harder to do it. And then this other article in the Harvard Business Review they looked across how long it usually takes to get the first machine learning MVP. And in most organizations, it takes between 4 months to sometimes a year to get the first machine learning MVP deployed. So it's quite a big lead time potentially. In software, now that we've matured with the practices of delivery, I think people won't be shocked to hear like Amazon deploying several times a day and you're doing like hundreds of thousands of releases every day. With machine learning, we're not there yet, but what we're trying to do is CD4ML is build the knowledge and the techniques to actually be able to do something like that.
Awesome. So now that Danilo has also talked a little bit about kind of where we're coming from with continuous delivery in general and also DevOps and so on, let me kind of explain a little or tell a little bit of a story where we come from when it comes to CD4ML, so applying continuous delivery to machine learning. And for this, let's get back a couple of years into the year of 2015. And it actually happened to be the first industry project that I was doing with ThoughtWorks. So quite a nice way to start my career at ThoughtWorks. And we were working for a client called AutoScout. And AutoScout is a online marketplace in Europe where you can sell your used car or where you can also buy new cars. So it's an online marketplace for cars and vehicles. And what we were asked to help with was to build a price estimation service and a price estimation page, right? So, so the idea was that you put in the basic data of your car on such a page, like what make, what model, and because it's about used cars, about the mileage, and then you can calculate what your car is still worth, and you can basically get a recommendation for what price you should put it on the platform. And so, of course, these days, this is nothing too special anymore. You see this with probably many online marketplaces such as eBay, etc. But back in 2015, this was actually still fairly new to bring machine learning techniques into production in a user-facing way like this, and user-facing way. And so when we started with this project, we basically started as two teams, right? So we had this team of developers, and I was a part of that team. And we were tasked to build that front-end application, basically, that users interact with. And then there was a team of data scientists that was tasked with building a machine learning model to predict those prices. And this back then, at least the initial versions of that prediction model were built using random forest, which is why I use a tree down here as an illustration for that. And kind of when we started with this project, we had this situation that there was literally a wall between those two teams, right? Because I think I remember we, the developers, we were sitting, I think, in the 11th floor, and the data scientists were sitting in the 9th or 8th floor. So there were literally, well, several walls between us, right? And that meant that we, as the developers, we would get an initial version of the prediction model from the data scientists, and then we would try to integrate it into our front-end application, and then we figure out something doesn't work well or it doesn't integrate well, and then we would send feedback to the data scientists, and then we would have to wait until something is fixed, etc. Right? And of course, for the data scientists, it was the same way. They basically had to wait for our feedback and weren't sure how to progress and so on. And so this really felt very sluggish and slow because there was just a lot of waiting involved. And of course, also some misunderstandings because, yeah, you were just kind of throwing your work over the wall, so to say, and then waiting for the feedback to come back a couple of days later. And so, of course, this situation that I picture here probably reminds you a lot of the situation that led to the invention and the culture of DevOps, right? Where you have exactly the same situation, where you have this split between developers and operations, and you get a lot of friction and frustration because there is a lack of empathy and a lack of close collaboration between those two different groups of people. And this is, of course, also what we felt because we were already used to do DevOps, and we were also doing DevOps on that particular project. And so therefore, kind of as a first step, we brought those two teams together, right? At least for the duration of creating an initial productionized version of that product. And that already helped a lot, right? Because this kind of closed the loop and we were able to iterate much quicker. And there was, yeah, it was just a lot more fun and we were far more productive getting this to be a great product. And so when we neared coming to a state where we wanted to release an initial version, of course, we felt then, well, as we're already doing kind of a DevOps culture here between developers and data scientists, of course, we also want to do continuous delivery. And there was, I would say, even something that we didn't think too much about back then, because as Danilo mentioned, we're used to do continuous delivery for ages now. And it's really just our default approach on every project. And so that was just the way that we thought, okay, so then we do continuous delivery here as well. And so then when we started setting up the continuous delivery pipelines, we quickly realized, okay, so first of all, we need several pipelines here. So we have our typical, let's say, web application pipeline down here that we're used to, where we build our application, create maybe a jar, and then deploy this jar on an EC2 instance so that it runs in the cloud. But then we need at least a second continuous delivery pipeline, which is building the machine learning model or the prediction model in a reliable and reproducible way, right? So we also want to put all those steps of model training and model building in such a automated or in a pipeline that can be automated. And so that means that then as a result of this, this prediction model pipeline, we have an artifact of the trained model, and now those two delivery pipelines, they even interact, right? So we quickly realized, oh, okay, things are actually a bit more complicated here. And we even figured out that there are more problems coming up that we didn't think of because we were just used to apply continuous delivery to, let's say, the standard software delivery process. And this is when we realized, okay, it seems that productionizing machine learning is actually hard, and applying continuous delivery to it, to machine learning. And this is where I hand it back to Danilo.
Great. So yeah, we'll talk a little bit about continuous delivery then. As I said, productionizing machine learning is hard. And if we look about like the reasons, what we want for production systems, we want them to be reproducible, we want them to be testable, auditable, and we want to be able to improve them continuously. And if you think about machine learning, well, it's non-deterministic, it's harder to test, it's hard to explain, it's hard to improve. So it brings a lot of challenges to the process. The other way we like to think about it is with machine learning systems, there are more sources of change that we have to look at. So first of all, the data itself can change, and change in data can be of various shapes. So the schema for the data might change. You add fields or you remove fields or things like that. But even if you don't change the schema, the data sampling might change over time. So the data represents different signals that machine learning models might pick up. And obviously the volume keeps growing over time as we collect and use more and more data. So that's one axis of change that's new. The other one is the model itself, because we will keep improving the model. New algorithms will be published. You want to try more training, maybe use newer data to train your existing models, or you're probably going to be trying out lots and lots of experiments. So there will be a lot of sources of change that the model will be evolving over time as well. And then, of course, the code, this one we know it changes over time for various reasons. The business needs will change. You might find bugs that we have to fix, configuration code that needs to change. So all of this adds to the complexity of change that we have to track. And if we go back to the definition of continuous delivery, Jess and Dave described it as being the ability to get changes of all types into production safely, quickly, and in a sustainable way. So we look at it as new types of change, but we do want to apply many of the same principles, because if we look at the principle level, most of them still relevant for machine learning systems. But if we can, we want to have a repeatable, reliable process. As Arif showed, we want to try to codify that into a pipeline. We want to try to codify the training pipeline maybe to make it reproducible so other people can train in a similar way. We want to automate as much as possible everything. Of course, some things are not easy or not possible to be automated. But as a principle, if we can automate, that helps a lot with the reliability and the repeatability. We want to think about quality and build it into the process. We like to work in small batches, so make small changes and release them rather than bundling up lots and lots of changes. We want to keep everything in source control, so we can go back and see who changed what or what might have triggered a potential issue. And we don't consider things done until they are released and released to the end user. And of course, improve continuously. So we want to be always finding ways to improve. And this is true for when we apply continuous delivery to normal software, and it's true, especially true for machine learning systems. You're on mute, Arif.
Thank you very much. Now that Danilo introduced a little bit what the things are that we want to take care of or that we want to reach when we apply continuous delivery to machine learning, let me run you a little bit through the end-to-end process of applying continuous delivery to to building a machine learning application. So a couple of slides here, we're looking exactly at those three axes of change that Danilo just mentioned. So the code axis, the model axis, and the data axis down here. And of course, it first all starts with the data down here, where we collect or where you have to collect training data, right? And you get this training data from data products, for instance, when you follow data mesh time also specifically. And then this training data is an input for the first phase of this process, which is the model building. And so, of course, another input of this phase is the training code itself, right? Which also contains the hyperparameters, all those kind of things. And so what you get out of this phase as an output is a set of candidate models. So this is not the model yet that you want to productionize, but just a set of candidates. And this set of candidates now is taken as the input for the next phase, which is the model evaluation and experimentation. Right. So I think model evaluation should be familiar to anyone who dealt with machine learning a little bit. You want to test how well the training worked. So you test your trained machine learning models against test data that you carefully separated from the training data to avoid overfitting. And then you get a couple of metrics such as accuracy, etc. And this allows you to both verify that the training was successful, or that kind of the quality of the model has a certain level that you want it to have. But also it maybe allows you to select one particular model of those candidate models. And you say, now this is the one that you want to productionize. And you can imagine that each of those phases here, those are steps in a continuous delivery pipeline that we want to be running automatically, so in an automated way, but where we have quality gates always between them. So basically, we don't want to go to the next phase, the productionization phase, if the quality of the model is not good enough, right? So we check about the quality of the or the result of the model training here. And if this is good, and if we decided for one particular trained model to be productionized, then we can do that, the productionization. And actually the productionization can mean different things depending how your system and your infrastructure is set up, right? Kind of a simple way of productionization could just be to package your trained machine learning model in such a way that it has the right format or the right size for your production environment, so that it can be digested by your production services. But what is also very often the case with productionization is also that you wrap your trained and selected machine learning model into its own microservice, so that you have a model service as the outcome of this productionization phase, right? So as said, it depends a little bit on your setup, but what you come out of in this phase is a productionized model in the form depending on your setup. And so now comes the testing phase, and this, to many people not familiar with the challenges in CD4ML or in machine learning, this could come a little bit as a surprise, because we already did model evaluation earlier here, right? So you could argue that why do we have to test again if we already checked the quality and the accuracy of the model? Well, a lot is happening here in this productionization phase. And depending on your infrastructure, maybe a whole service has been built around your model, and a lot of things can go wrong, right? So you need to make sure that the productionized model actually shows the same behavior that it showed during model evaluation and experimentation. So you want to use, for instance, the same test data here that you used for model evaluation, and check whether you get the same results from the productionized model as well. And this means also that you have to use some test code here. You also want to test other parts of the productionized model. And then what you get as a result of this phase is now a productionized and tested model. And so again, only if all those tests go green, then you're allowed to progress to the next phase, which is now the actual model deployment, right? So now you deploy this tested and productionized model or this model service into the production environment. And that often means that you bring it together with an application that is consuming that productionized model. So now you have basically this other pipeline coming in that I was sketching out earlier. And you often have other applications that now get deployed together with this. And so then what you end up with is a model and a model service that is now running in production and can be used. So now you could think that this is the end of the story, but it's actually not at all. So now as a phase after this, you need to look at monitoring and observability. So you could say that the interesting part actually only starts now, because now the productionized, tested, and deployed model is facing the real world, and it's facing actual real world data, and you need to check how it's behaving in the wild. And this in turn means that you're generating data now again, right? It's running with actual user requests now, and you can and you should collect this data. And this data of observing your productionized model then feeds back into the first phase of this process, which is the model building. So you should use this data that you collected in the wild to update and retrain your model so that it's still the best fit for reality, so to say. And so therefore what you get is a continuous loop where you continuously improve the quality of your model. So now, as has been mentioned before, the idea of DevOps, the idea of continuous delivery, is to automate as much as possible, right? So we want this whole process to be automated. And actually automating this is quite a lot of work, and it needs the right tools, technologies, and architecture decisions to do so thoroughly. And I think this has also been mentioned in the introduction. We have written an article at martinfowler.com where we outline the details a little bit more about this. But to give you an idea here about the topics that you need to cover to automate this end-to-end, here are many of those topics that we figured out that you need to take care of. So to just name a few here, of course, you need to have your data discoverable and accessible. You need to have the right tools and infrastructure to do reproducible model training. You need to be able to track your experiments, and you need to have an elastic infrastructure to ramp up your model serving infrastructure and ramp it down again. So you need to do model serving, you need to do model deployment, of course, and you need to do testing and monitoring. So as we don't have enough time here to go into each and every one of those topics in depth, we selected 4 of those topics to talk about them a little bit more in detail. And those 4 are version control and artifact repositories, monitoring and observability, then testing and quality in general, and model deployment. So let's go right into those 4 then. So let's start with version control and artifact repositories. So basically what you want is you want to be able to keep track of all the types of changes and of all the artifacts that you are generating over this whole end-to-end process, right? So Danilo mentioned before, continuous delivery is about keeping track of all types of change. So you need to be able to track all those types, and you need to be able to manage the artifacts that are being created. And in many cases, because we have more different types of artifacts here, we often need specialized repositories for the different types of artifacts. So to give you just one example, we realized quite quickly that you cannot just put large amounts of training data into Git, right? And the same goes for the trained machine learning models. You cannot just put them into a Git repository, because that's not what Git is built for, right? So instead, you need to have specialized repositories, similarly as you use specialized repositories for Docker images, etc. And then you need to kind of reference those artifacts from your version control system so that you can still trace kind of the path of those dependencies. And if you then, with such a system for version control and a set of artifact repositories that you link together, if this allows you to track all the dependencies of an artifact, this means that you only need to rebuild artifacts selectively when their inputs change, right? So looking at this graph down here, you could say, for instance, that the training data here is a result of the decision of sampling and the decision of the schema. And then the trained model is a result of the training data and the machine learning code, right? And so those are the inputs to that artifact. And then finally, as you've seen, this is a kind of only a simplified illustration. You have the trained model and, let's say, for instance, a Docker image as the inputs for the running model service. And if you track those dependencies, that means that, let's say, if something changes in the Docker image for the model service, then you do not need to retrain the model here, right? Because you know that nothing has changed here. So you can take the same artifact from an artifact repository, or in this case from the model repository, and redeploy it with the new version of this Docker image so that you get an improved version of the model service. And this is what I mean when I say kind of when you track the dependencies and the inputs of each artifact, then you only have to rebuild the parts that are that really have to be rebuilt. And basically, the more fine-grained you go with this, so kind of the more specific you go with versioning decisions, basically, the more efficient you can go here, right? So for instance, also when you separate the sampling of the data from the schema changes, that also allows you to be more specific with tracking your changes here. So moving on to the second topic that we wanted to talk a little bit about is monitoring and observability here. And I already mentioned this when going through the end-to-end process. A live model, a live machine learning model, lives in a changing environment, right? So it lives there and it needs to adapt because it reacts now to real-world interactions and real-world data. Now, as with any distributed system that is running in production, you of course need to monitor its basic health. And to a certain extent, that is relatively easy these days because we have a lot of tools and you can use to some extent generic tools to do this basic health monitoring. But then when running a machine learning service in production, there are other questions about observability and monitoring that are a bit harder to manage. So for instance, how can we know when a model has become stale, right? So how do we know that we actually have to update it? Of course, we could be reluctant and just say, well, we just update it once a week. But in fact, different applications of machine learning vary a lot in their requirement of how often a machine learning model needs to be redeployed and retrained, right? You have some applications where your model doesn't need to be updated for months, because you could say that the environment doesn't change that quickly. But you also have other cases where you need to update your machine learning model basically every minute, because you have user interaction and you need to make sure that it's always up to date with the latest interactions. So therefore, what you want to monitor is really how is it reacting now to real world data, right? As opposed to the training data that you used. And this is a bit more complicated because in many cases you don't have labeled data now anymore, right? You don't know what the correct answer is. So one thing here is to look at your users and actually check how much trust, for instance, they are putting into your production model and what feedback they are giving to you, maybe implicitly. So for instance, back when we deployed this price estimation service, we were looking, so we were giving a recommendation about a price, right? That people should put their car on the platform with. And this was just a recommendation, but we could also track then what price they would actually choose. So depending on the distance or the difference between this recommendation and the price that the users actually were choosing, we could see kind of how much they were trusting our recommendation. And then if we see that this trust is going down, then we realize, okay, maybe the model is going stale and needs to be updated, or we need to even change our approach a little bit here and make sure that it's still the best solution to the problem. And kind of this is just one of the topics there. Another topic that is even harder to tackle is if you now update a model on a continuous basis, so you update and retrain it really often to make it better and better, how can you actually ensure that it's moving in the right direction, right? So model drift is the key word here, where you want to make sure that you do not optimize on certain metrics, but in the end, you end up basically in an over-optimized situation in a direction that you didn't want to go into. So you need to set up some more holistic monitoring to make sure that you're doing this correctly. And yeah, with this, I'll hand it back to Danilo to talk about testing.
Cool. Yeah, testing these types of system is much more complex. You might be familiar with the idea of the test pyramid for code, which is the blue corner there in the image. But when we're thinking about data and model changing and how the interaction between them happens, there's many other types of testing that we can try to add into the process. I don't have time to go through detail, like all of the different types of testing here. I actually had a whole nother talk just talking about this topic, but just to give you an idea for how these things interact, right? You might train your model and assess the quality of the model, how the model is used with the production code. You can do some type of contract testing to make sure, let's say you train a new model and it needs a new feature, but the production code is not set up to pass the same feature, then you kind of break the contract. So we can write some more automation to try to catch those things before they hit production. And then you're always going to have to do exploratory tests at the top, right? Like these systems are so complex that it's really hard to automate everything. You want to have some human in the loop to catch edge cases. The other topic I was going to talk about briefly is model deployment, which is basically assume we have a model, how do we replace it with a new one? And there's a few different approaches. So one approach is you have this maybe like a serving API for the model, and behind the API, you actually, instead of having one, you have multiple models. And depending how you implement, let's say, just as an example, we are trying to train a model to give pricing recommendation for different products. You might train separate model for each product or a different category of products, or you can try to train one model to be able to cope with any different types of products. So behind, if you're working with this kind of API, you can manage that and make that decision transparent to the user, whether you're using one or multiple models. The other approach is you want to try to maybe do like a shadow model. So you have the current model that's live, but then behind the API, when you serve a new prediction, you also send that same data to your new model that's running side by side, but is not actually being used. So you can capture some data about how it would have performed before you make the decision to actually flip and put the new model live and replace the existing one. So this is a technique that we've seen used. And then more complex, you can actually have competing models in a way that you can tie back to some kind of reward and then use data or this feedback from the user to decide which model is performing better. So it's kind of like an A/B test in a simple way, but it could be something more like a multi-arm bandit or different kind of approach where your routing logic will use that information about how the model is being used to decide which one is performing better in production. And that leads me to the next section to conclude, which is we want to talk a bit about the future challenges and opportunities. And one area that's quite interesting is how do we bring the idea of reinforcement learning into CD4ML? Because you might have guessed, as we try to improve more and more the feedback, it gets to a point where we're trying to actually react as close to real time as possible. So if we look at the usual process, right, like we usually capture training data and then we learn from that data and then we deploy it. And then once it's live, we'll capture more. But there's one missing ingredient here, which is how can we use the models to explore a little bit and try different things and learn from that environment. So as an example, if we build a recommendation product and we train it based on my previous history, maybe it will recommend things similar to what I bought in the past. But how is a recommendation model will be able to explore, like maybe I have other interests. I might be interested in buying something that I haven't bought before, but it's something that the model wouldn't have picked up from the previous data. So what we want is to be able to learn this correct signal and try out different things, sometimes things that we haven't actually seen, so that the model could explore that and improve based on that feedback. And this is where reinforcement learning kind of comes into play. But implementing reinforcement learning is hard. I'd say even harder than what we discussed so far. Some of the challenges, for some problems, there's basically too many possible states that we have to explore. So it makes it really hard to train it. For many cases, like reinforcement learning for a game, or we see a lot of examples where it's trying to emulate physics of the real world, then we can build an environment simulator where we can basically let the model learn by running against the simulator to be able to explore all these different states. But many real world examples, we cannot build a simulator. Like, how am I going to simulate my buying behavior? If I knew how to write the simulator, then I knew the logic. So it's really hard to have a simulator for some of those scenarios. And the other hard thing is linking the rewards to the action. So if we track, let's say when I click a recommendation, if I actually bought it, that would be feedback that was a good recommendation. But did I buy it because it showed to me right now? Sometimes I might see it today and I'm not going to buy it until much later in the future. So it's really hard to assign that reward. But this approach is too promising to give up, even though it's hard. So what we've seen is we can actually try some simplifications that will still make it very valid to solve a big portion of real world problems. So as an example, we can maybe simplify it to assume that the reward is going to be revealed almost immediately for an action, which is not technically true. And we can also attribute the rewards to the previous action. So we don't have to think about all this history. and using something like contextual bandits, that we can try to use this feedback to choose the model. And you can see in the right side, we try to put some examples of problems that we can use contextual bandits. An example might be dynamic pricing. So if you're trying to choose the pricing of a product dynamically, you want to try to learn them, you want to try to explore the different types of prices, because you never know, for instance, when you recommend the price for the car, they pick a price, but you don't know if they would have bought if the price was a bit higher or you went a little bit further in the threshold. So you want to be able to try different things and explore those problems. So as an example here, how we can implement a contextual bandit architecture, we'll have our prediction API, which is serving that prediction. So the user will make a request, and you see here like X represents some kind of context from the environment, and we will recommend back an action, and we'll send them back an ID for that prediction. And you see why we need the ID later. The other thing we'll do behind the scenes, we will track in a kind of a joiner, a separate service, this ID, what version of the model it was, what was the timestamp when we've done that, what was that context where we made that prediction, what was the prediction that we made, and then the policy or the model itself that we used to make that prediction. And we have another API that we'll be able to track, and this is why we need the ID, what was the reward. So did the user actually use that prediction? So we need to be able to link back, and we send that along with the timestamp to the joiner. So we can create that view of, okay, for this prediction, we had this reward at this point in time. And what we'll do, we use some kind of object store that we can keep track of the historical, this historical data about what we predict and what the rewards were. And then we can use a learner system, and it can work either in an online way, where it uses this joiner service to learn as things are happening, or we can retrieve those tuples from the history in the object store that we can train them offline as well. And we're usually going to store the output policy of the model itself in the object store, and then that model needs to be deployed into the prediction API using the contextual bandits idea that I talked about before. So it's a more complex architecture trying to do this, but there's a lot of potential benefits trying to apply this approach, and we're exploring that, how to make that reproducible as well and shorten the feedback cycle.
Oh, awesome. So now, kind of coming from this, really challenging but also exciting view on what the future brings. Let's, before we wrap up, also have a look at really open challenges that we still have. And this brings me to one particular problem, which is that a lot of the very well justified criticism about machine learning systems is actually based on a lack of trust into those systems, right? And here on the right, I don't know whether you know this example, but this was posted on Twitter maybe a year or two ago, and it shows the result of a depixelization service, basically, where you can put a low resolution image of a person as the input, and you get a higher resolution estimation of the face of the person, right? So it tries to bring back the higher resolution. And probably, as you can see on the left, you see a pixelated picture of former US President Obama. And then on the right, you see the result of this kind of scaling up. And this becomes suddenly the picture of a white man. And so, of course, this is a big problem, but and it's not good. But to people who understand how machine learning works, this maybe is not a surprise, right? When you know that, when you understand that maybe this model has been trained predominantly with pictures of white men, then you understand that it's leaning towards giving such a result. But many people do not know this. So a big task here is on explainability, right? So we as practitioners and people bringing this into production, we need to work on being able to explain how a model is coming to its conclusion. And we also need to be able to explain its limits, right? And also many of those issues also cannot be solved by technology alone, I would say. So for instance, when dealing with such biases, I personally would, for instance, often look at the composition of the team building that service first, right? And maybe have a look whether there is a good diversity in the team building such a service, because otherwise it's always hard to sustainably make sure that such issues can be avoided in the future. But beyond such cultural and organizational approaches, there are also technical ways to approach those challenges, right? So for instance, with explainability, there are even approaches out there to deploy explainer services and even to monitor explainability as kind of a way to reverse engineer how a model came to its conclusion. But another good way is also to break down one large model that is hard to explain into several submodels, right? And then maybe when you have the different submodels, then you can explain better how each of those submodels is coming to its conclusion. And then you basically just put their results together, and this makes it much easier to explain how the overall system came to its conclusion. And this brings me also then naturally to auditability, which is another big and open challenge. The more machine learning systems we bring into production and build important real world systems with. So I already mentioned this here. How can we ensure that a model does not become biased, right? For instance, and in fact, applying continuous delivery here for machine learning can both help to prevent such issues, right? Because you can put technical measures in there to test the quality and even test bias before releasing. But maybe even more importantly, you can trace back to the reasons when such an issue appears. And that's even more important for auditability, because as with security topics, it's often more important to understand how a system got into the wrong direction, to be able to prevent that someone tampers with the system and is able to move it into a direction that you don't want it to go to. And so this is where we feel this idea of tracing the inputs that make up the different artifacts and being able to trace this from end to end, so that you exactly know how you came to a certain version of a certain artifact, can help a lot with this auditability. And with this, I would like to thank you a lot, everyone, and maybe we can still answer a few questions. Thank you.
Okay. Thank you very much for this very interesting and exciting talk. We have time for some questions. We will go running over time, but we have very exciting questions here, so I want to go through it. Maybe first, jumping on your last statement about how continuous delivery can actually help mitigate issues like bias, because you can trace, right, the root cause of some problems, some drift in your model. But I want you to reflect on the fact that we're seeing more and more regulations on how much data we can collect, right? How much we can keep, how much information we are allowed to keep on our customers, which is actually critical to this type of diagnostics, right? So how do you see this regulation like GDPR interfering here, and what do you think could be way arounds, right? This to still make sure that we can reap the benefit of this full traceability that we could have in this.
Yeah, maybe I can quickly answer to one part of that and maybe pass it over to Danilo. Because that also matches quite to what I just finished with. What we do not want to have is basically get a one-time certificate on a trained model, right? And say, okay, this has been certified to have no bias. And then we're never allowed to touch this model again, right? Because then we cannot improve on the model and we basically cannot build useful production services. So what we would rather focus on is on certifying the quality control process, right? And kind of looking at the whole process and make sure that there are the right things and quality gates in place to make sure that if things go downhill, so to say, that this is not just going to the public as is.
Yeah, touching on your question about regulation, I think it's quite important because things like GDPR, like they actually they require you to be able to explain if you're using a model to make a decision. So what that means is, I think there's a lot of research going on in the explainability and explainable AI space. I think you had another speaker talking just about that. I think that field is going to keep growing, but it also limits, I guess, the types of models you could use. It's like if it's really like a black box, very hard to explain model, you're probably not going to be able to use that if you're under regulation. And the other thing is capturing of data. We do this a lot with clients, like how we design the data platforms, how do we build the security controls, and like who has access to what data. That's a whole nother topic. Like in here, we show as discoverable, accessible data as one component, but if you unfold that, like how do you actually build a secure platform to complies with the regulation? That tends to be like multiple years projects where we're helping the clients build that.
Yeah. Okay, exciting. So let's jump to some questions that we have in the QA. So first question, it's very popular from Christian, right? His point is, in this field, we went from having basically no tools to having too many competing tools now, right? And he said, are you anticipating any standardization going forward? Like do you have any specific recommendation toward tooling?
Yeah, I agree with the explosion. I think it's a natural cycle for any like new technology. If we look at, like the JavaScript ecosystem, or even in DevOps, the growth of Docker, Kubernetes, they always go through this kind of explosion phase, and it tends to consolidate after a while. But I don't think we're there yet in machine learning. There's lots of, you see like vendor products and open source products trying to solve pieces of this puzzle. And what we tend to do, like we like to favor open source solutions when we work with clients, because a lot of the vendors, they will try to solve everything. And as you saw, there's many different pieces. It's really hard to have a tool that will really solve everything well. So we prefer to try to use the best tool for each type of problem. So yeah, in terms of recommendation, I think if you go in our article that we wrote in the Martin Fowler website, we had a sample GitHub repo that we walked through, like an actual example, and then we had to pick some tools to do that. I wouldn't recommend say like, yeah, this is the best one you should always use, but it's good to have a view of the different options, I guess.
Yeah. Interesting. So jumping on, following up on that, we have a question from Bram, which is really tapping in your wisdom. Like, based on your experience, what do companies struggle the most when going from continuous delivery to continuous delivery for ML? Like, what's the ML effect that coming?
Yeah, I think the challenge is more not continuous delivery to CD4ML. It's more whether they're ready or they understand using ML in the first place. Because like the continuous delivery part is if they are used, if they know where they're going to apply machine learning, then it tends to be our approach to do it. So it's not like the challenge on its own, but we have a lot of clients that are either not comfortable or they're not ready to trust a machine learning kind of model. And we still have lots of those conversations. I was on a conversation this week where they're like, yeah, we're not mature yet, or we don't trust because it doesn't work 100% of the time. There's a lot of misconception. I think people that don't understand these systems, how useful they can be, even though they're never going to be 100% accurate. And that tends to be the bigger challenge that I see. It's people being comfortable using this and trusting, I guess, the machine learning system.
Yeah, and I might add to this that my feeling that it's probably more that, or it's often that basically companies that struggle with continuous delivery in general, they of course will also struggle with continuous delivery for machine learning. So you need to have the foundations there and the right mindset so that you understand the challenges of continuous delivery in general. And although we're practicing continuous delivery for ages now, there are still many companies that only do continuous delivery on a certain surface level, so to say, which can be improved still a lot. So I would probably say in many CD4ML projects, we're still working on the basics to get the basics right, and then turn towards the specific challenges of CD4ML.
Okay, so we have a set of questions coming from YouTube about the retraining, the continued learning, and also about like tracking for distribution shift, right? And so one question is there any standard technique that you have seen in the industry or from your experience being used to actually detect for distribution state shift and track like stale models, like any specific recommendation that you could do on that? And then they have follow-up questions that comes from the fact that sometimes in production, you can have very large complex model, then retraining them can be quite time consuming. So the two questions, I guess, it's what would you think is the more appropriate ways to handle this, like in a realistic way, right? Like how to make this process efficient from your experience?
Yeah, the tracking the model drift, there are tools existing, like even open source ones, where you can track the you're trying to link what the model predicted, I guess, based on the inputs data and based on the context. And then it's almost like if you capture that and you stream that somewhere else, you can have another system that's monitoring it side by side to production, and then you can apply explainability metrics maybe on that data, or you can track the model drift. The last one I saw, just to be specific, like there's a set of tools called Seldon. They have a bunch of libraries for explainability and also for model drift monitoring, and it's open source. So I would maybe recommend having a look at them. Seldon.
Okay. And I guess the other question was on the size of models. Like when you deal with large deep neural networks, should you retrain them frequently and it's expensive? Like what kind of techniques to handle or circumvent this issue from your perspective?
Try go about that. So I think, we work with our clients to solve problems, right, and to create value. So realistically, very often the more simple solution is the better one, right? So I think if you come maybe from an academic background, you might be disappointed on some occasions because it's just often the right decision to go for the more simple and also more easy to deploy solution, right? Because in the end, it's important to create value sustainably. And if you have maybe one solution or one approach that gives slightly better results, but makes it harder to maintain those results in production, then you would usually go for the more simple solution. So I guess we're being very pragmatic about this.
Okay. So we're almost way over time, but if you don't mind, maybe we'll pick one last question from Marco Vigiato. Marco is asking, can you give example of production data that can be used to automatically improve the deploy model? For example, if most recommended products are not bought, how can we use this information to actually improve the model? Right? Like the signal that you may be getting from the field may be also heavily biased or incomplete in most cases. How do you use this, or how can you manage to use this to improve the model? I guess if I capture the spirit of Marco's question.
Yeah, if it's not bots, then you don't have that data basically. Like it's I was talking to my colleague the other day, like he was working with the clients trying to solve, I think it was like customer acquisition problem. And they were trying to train a model for like, okay, when the user doesn't subscribe, we want to train a model that will predict when they're not subscribing. And we're like, you probably don't have that data, because if they haven't subscribed, then you don't know what's driving them to subscribe or not. So this type of thing is tough, I think, to improve, because a lot of the time you might have a bunch of data, but it doesn't have the right signal that you're trying to train. But in terms of the automatically improving, I think a lot of these online learning models, the reinforcement learning, they are in effect learning in production. And it comes with a bunch of challenges. I briefly touched on it, but like the versioning there, it's really hard, because if the model is improving in production, it's not like we're placing a version tag every time it gets retrained, because it might change every new data point. It would change a little bit. So what we tend to do is logging that data and how it's affecting it, so you can reproduce it later, rather than trying to snapshot the model in production and keep track of that version in real time. It's a lot more complex. So it's if you can, like Arif said, like a lot of the time a simpler model will work, and having the CD4ML process where you train offline and then you deploy, and as long as that feedback loop you can capture and do that relatively quickly, it tends to work for majority of our clients' cases. But if you're in a niche space where you are doing online learning, reinforcement learning, then that model doesn't work quite as the same way. It needs to be tweaked.
Thank you very much for the very interesting talk and exciting discussions. And I think we'll wrap up here.